Okay, example number two. Like example number one, all right, read the problem, wrote out the givens. You guys can pause this and do that. And we now have our pulley, which is mounted from the ceiling. So the earth is pulling down on the pulley itself. We have the 3 Newton weight pulling in the opposite direction in which it's moving. And then we have the axis of rotation, that the center of that pulley, all right, wherever that axis is, pushing up, preventing that entire pulley from falling to the ground. So looking at this, we clearly marked where our axis of rotation is. We have one torque exerted on this. So again, we look at this in terms of Newton's second law of rotation. So the net torque over the inertia, very similar to force over mass, will equal our angular acceleration. In this case, we have a force exerted of 3 newtons exerted at a radial distance of 0.5 meters from that axis of rotation, divided by the inertia of the object, the angular equivalent of mass. Okay, so the difficulty or ease of which it rotates. So when we make this, we find out that the angular acceleration is going to be 2 radians per second squared, which is in the opposite direction of which we defined as positive is counterclockwise. Now, sign notation, one's positive, one's negative. It's up to you. In this case, I kept counterclockwise as positive. So we have an angular acceleration here. The pulley will slow down and eventually come to a stop before it reverses direction and goes the other way. So to address the other questions here, how long will it take for this to stop? Again, very similar to our motion equations, we can use our angular motion equations, our angular velocity, final velocity, which if we're looking for it to stop would be 0 radians per second, is equal to our initial angular velocity, 4 radians per second, minus 2 radians per second squared times the time. Solving for the time, we get 3 seconds it takes to stop. And then what is the angular displacement? So again, very similar to regular motion, you have your initial position or your final position is equal to your initial position plus the initial velocity times time plus 1/2 at squared. So we have our angular equivalents too. They essentially want to know what the angular displacement is. So it would be your final position minus your initial position, our final angular position minus our initial angular position plus our initial angular velocity times time plus 1/2 at squared, or angular acceleration squared. So with this, we don't know what our initial position is, so we'll just call that 0. We're really only curious about the final angular position. We know the initial angular speed is 6 radians per second. It took 3 seconds for it to stop, plus 1/2 times the negative 2 radians per second squared times 3 seconds squared. So we have 18 minus 9 is equal to 9 radians would be our angular displacement. Our graphs, if it's rotating and slows to a stop, our velocity versus time graph would be a diagonal line. Our acceleration versus time graph is constant and negative. So your two graphs would mimic, again, velocity and acceleration if it was linear, but we're just going in circles here.